please be seated. Okay, good afternoon, everybody. For today's lecture, I'm going to talk about dynamic traffic assignment, DTA. And I'm sure that it's very similar to GIS, that most of you have learned traffic assignment already in Dr. Wang's class. And some of you have no idea what they are. So it's very difficult for me to prepare. So I want to make it interesting. Today's outline is like here. So I want to spend some few minutes to talk about the concept first. Then I want to want to show you to demonstrate how to do that in Reason, which is not very easy. And I want to briefly introduce M-sum, COSIM, and parametrics DTA models. And in the next lecture, I'm going to talk about transients DTA. It's so complex, so I want to put it in a separate lecture. So traffic assignment, as I already mentioned, I mentioned it several times. Traffic assignment. For traffic assignment, we have some inputs. The inputs include two important parts. The first part is called zonal trips, or OD matrices. So we know we have several OD matrices. Each OD matrix represents the total number of trips between each OD pair. Other than that, we need an abstract network, which is the link node graph, like what we used to calculate shortest path in the last lecture. I want to emphasize it's an abstract network. It's not a realistic network. Because in this network, we are not going to consider or taking into consideration the signals. Because we don't have the ability to do that. And the output is simply a lot of paths. To do traffic assignment, traditionally, we use so-called volume delay function, or VDF. This is a function between the volume of a link and the delay or travel time of the link. And traffic assignment can be categorized as static or dynamic. Okay, so that's the first important concept you want to understand today. The first important pair of concepts. Static traffic assignment means the assignment doesn't consider time. Dynamic means it considers time. So what's the difference? The difference can be easily illustrated by this diagram. So we have a start point, we have the end, an end point, or this is an OD pair, and we have several possible paths. And we say the delay on each link or delay on each path is a function of the volume. Then when we do traffic assignment in a static way, we think there's no time. Because there's no time, everything happens instantaneously. Which means when you assign some volume to this path, the result will be the delay of this path immediately changes, and the change lasts. In another word, there is no dynamic movement of vehicle or traffic flow. And what does this indicate? This indicates if you put some volume to this path, then all the links along this path are affected immediately and forever. So let me give you a simple example. Suppose we have two paths. Okay, suppose we have one path between an OD pair, and it's a bridge. The bridge can only accommodate one truck, but we have two trucks going along that bridge. So will the bridge collapse? In static traffic assignment, yes, because both of the trucks are assigned to the bridge, and the bridge can only accommodate one truck, so it will collapse. But in dynamic traffic assignment, we consider the factor of time, which means the two trucks can go there one by one, so the bridge can still carry both trucks. Okay? So that's the concept of static and dynamic traffic assignment. Just remember, in dynamic traffic assignment, we consider the temporal factor. In static assignment, everything happens immediately and lasts forever. And assignment is not a problem. We can assign as we want. We can use our method to assign. But in transportation, in the field of transportation, as early as in the 1950s, there was a person called Wardrop who developed two principles. And he thought those principles are reflecting the truth of transportation. The two principles are system optimal and user equilibrium. In system optimal, the total travel time of the system, of the travelers in the network is minimized. In user equilibrium, any individual traveler cannot travel faster if he or she switches to another route. They look very similar. I mean, if you look at them for the first time, you may think they're almost the same. But actually, according to the mathematical formulation, they are different. Somebody called user equilibrium as user optimal. And that happens in some literature. So these are the two definitions of UE. The importance of system optimal and user equilibrium is that they can be calculated sometimes. And people tend to think that they represent the truth of transportation system. So when we do static assignment, sometimes we want to seek the OE solution. We want to find the UE solution. Sometimes we want to find the SO solution. But that's the thing you know. But today I want to criticize a UE because it has a lot of limitations. First of all, it's using an abstract network which doesn't consider anything like the signals or stop signs or turnings. The second thing is a simplified world, including the demand, including everything. I mean, the turning and the data. The data comes from OD matrices. They are also simplified. Let's say we use the traffic assignment in the last step, as the last step of 4-step models. And let's assume that in each step, we have a uniform distribution between the 80% and 100% of the real value. So let's say in the first step, we should get the correct result is 100, but we may get anything between 80 and 120. And if we accumulate these impact, what's the precision of the fourth step? So it will be, so in the first step, we'll get a distribution between 80% and 120%. This is the arrow, so this is the result of the first step, or accuracy of the first step. After the fourth step, the error accumulates to the power of 4, which is equal to almost 30% something. And this is equal to almost 200%. So let's assume our data is having a very high accuracy. After the 4 steps, we are going to get very low accuracy. And another thing is perfect information. In user equilibrium, when we solve it, we always assume the users, the travelers, are having perfect information, and that's not true, right? And we assume the system is stable. So in the first day, you travel along this path. Then in another day, in the second day, you want to try another path which is better. And this requires a stable system. Because if the road changes every day, or the users are changing every day, then how can we finally reach this user equilibrium? And the most critical thing is it's very difficult to calculate. So in the case of dynamic traffic assignment, we want to reach user equilibrium. Okay, let's distinguish these two concepts. Dynamic traffic assignment is the method you are going to use. And the result you want to reach is called user equilibrium, or dynamic user equilibrium. But nowadays, even nowadays, after several years of research, people are still finding it so difficult to calculate dynamic user equilibrium. Now the question becomes, if so many smart people using the state-of-the-art algorithms and computers are unable to calculate this user equilibrium, then how can those not so smart travelers reach this user equilibrium, right? So this is the limitation of UE. So I'm doubting if it really exists. But this, although we have some criticisms, we don't have better solutions. So that's very embarrassing. So if we don't have better solution, then we just keep on research about this, right? And because we have so many transportation graduate students, we have to do something. So let's keep on doing some research about user equilibrium. And here is a sentence that was supposed to be said by Feynman, Richard Feynman. He said, philosophy of science is as useful to scientists as ornithology to birds. Ornithology is a branch of zoology, which studies birds. Okay, so philosophy to scientists is as useful as ornithology is to birds. But I would say both of these are more useful than user equilibrium is to travelers. At least when you do some research about ornithology, you know birds. The birds don't know you, but you know birds. But when you're doing research about user equilibrium, you don't know more about travelers, and travelers don't care. You don't even care about this. So I would say, I don't want to put into the slides, but today I would say user equilibrium to transportation engineers like us is a religion. So you have to believe it, and you do some research. And that's the status of those research. So before I go to the next slide, let's just believe in user equilibrium. And let's see how we pursue user equilibrium in our simulation models, okay? So the first thing I want to talk about is the dynamic travel assignment in VSIM. And the purpose is to find the user equilibrium. And it can be summarized by three things. The first thing is using generalized cost. So for each path, each link, in the last lecture, I was talking about shortest path. And in order to calculate shortest path, we have to assign a weight to each link, right? And in VSIM, it's using so-called generalized cost. This weight is generalized cost. I'm going to explain that more in the following slides. And the second thing is path finding. As I already mentioned, it's very difficult to find the k-shortest path. And how does VSIM solve this problem? VSIM does it by a learning process, which I'm going to introduce also. The third thing is, if you have already found several paths, how do you choose them? And VSIM is using a discrete choice modeling method, and I'm going to talk about that too. So these are three essential factors of the DTA in VSIM. In VSIM, I think you still remember in transims, all the trips are between activity locations. And in VSIM, it's very similar. So the trips are happening between parking lots. There can be three kinds of parking lots. The first one is called a zone connector. The zone connector is an abstract idea that when the vehicles are approaching this zone connector, they don't slow down, and when they reach the middle point of the zone connector, they disappear. So this is